me know if you need something else. Sorry about the delay.
Okay, so welcome to the joint group meeting. Today we have a special speaker, Daniel Ramirez, who is practice of the second year seminar, which is a requirement of the Department of Chemistry and Biochemistry. So, if you are close friends with Daniel, try to be aggressive and ask him lots of questions. It will help him in the future to improve it and perform outstanding on the actual presentation. Yes?
Do we wait till the end or in the middle?
In the middle it is more funny, more interesting.
I just have a comment right away. So in the second year, you're not expected to show your data or your results.
Yeah.
Which means...
Let him present everything.
Yes, this is only...
Exactly.
Which is not yours, and starting on this page, this is your results. This is not the format of the, and not the purpose of the second year seminar, it's only literature review.
I thought that the department also said that it couldn't be on your main research topic.
No, they changed it.
Oh, they changed it. Okay, so it can be on your main research topic.
Yeah.
Okay.
And mini and maxi now also can be on your main PhD project.
Oh, that is lame. That is so much easier.
Except that now mini and maxi has to be done by 6th semester. He is expecting to have mini and maxi in spring.
Oh.
Because now it's related to your PhD project, so it's just a piece of cake, right?
Hopefully. So that has now been voted in. Oh, wow.
This is already the policy. If I think he's lucky, he can choose the old policy, same as you were working on. I think you still have a choice.
That's what Dr. Rogers told me.
27 credits, I mean, as regular one, right? And then I guess your mini maxi can also be in a third year, according to the old policy, right? In a third year rather than second year. Or you can choose 20 credit policy and then your mini maxi has to be done this spring.
Oh, now the new students only need 20 credits of lecture?
Just 4 core courses. Inorganic, organic, physical chemistry, and the critical chemistry, which is called, with a beautiful name, Advanced Survey.
Oh, so
Advanced Survey in Analytical Chemistry, in Physical Chemistry, in Organic Chemistry, in Inorganic Chemistry.
Oh.
Which is already the title, survey something kind of introductory part, right? And advanced means it's beyond introductory level. So we already have contradiction in the title right away. But this is how it works.
I guess
now.
if they need to, yeah, okay.
So for the purpose of today's talk, I'll be mentioning a brand new material called perovskites. Well, not that it's new, but it's just getting a bunch of traction in just recent years, where it started off at a low percentage of yield of photo conversion, about 2.9% when it was first introduced, like in 2011. And then in recent years, it's been, well, up to currently, it's been around a percentage of about 23% conversion rate. So in just less than 10 years, it's seen almost a 20% increase. So hopefully, if it's continuing such a bright future, we could probably see up to conversion rates to about 30%. But yeah.
So on slide 5, you show that.
Just a second, slide 5? We still have slide number.
Yeah, I know, but he shows the graph of conversion.
But it's too early.
Let's
wait till...
I probably want speaker to move slide 5 into number 1.
No, but why introduce, like, why say what entire slide is about and then go back to what the slide says?
Just a quick.
I mean,
As an
it's
abstract?
too early to say anything
Okay.
what he's saying. He just started with the title. Let's give him a chance to at least speak for a couple minutes to see where he really wants us to, where he does lead us.
So normally, there's a couple of normal sources of energy that are being utilized today, renewable and non-renewable. The point to well, the goal of the research of perovskites is to try to move away from non-renewables and dangerous sources of energy such as uranium and coal. Everybody knows about coal. It's basically the number one, well, the number two behind petroleum, or three, actually, I apologize, for sources of energy, where coal, usually, we all know it gives miners black lung. It's a really dangerous way of obtaining it. And, well, we have natural gas, that's obtained by fracking.
Is it dangerous?
Excuse me, coal?
It's dangerous to be in the mines, or what do you mean by dangerous?
Yes, it's dangerous to be in the mines. You also usually hear every now and then in the news a mine collapses, and then they have to now send a rescue team to try to extract miners that are stuck inside set shafts, which is a bad thing. But also natural gas.
You sound now like you are from some union, like working union or something. Fighting for the rights of workers in the mines.
Yeah, this is true. And with natural gas is obtained by fracking. I'm not sure if it's been proven that fracking causes earthquakes, but if it does, we all know how dangerous earthquakes are. We can look at states like California and that deal with earthquakes all the time. Well, petroleum.
It's not just trade union agent. It's like a lawyer who's making the case.
And with petroleum, wars are still being fought over this resource. So if we can move away from oil, that'd be nice. I mean, Tesla's making a good choice, trying to move away from petroleum-based cars. Also, there are natural gas cars as well, but once again, I said that leads to fracking. Uranium, we kind of know that.
Just a second, but what's the problem with oil?
With oil, wars.
Ah?
Wars are fought over oil. A normal joke that people say is when America sees their oil in other countries, they want to give them freedom.
Ah, so now you're becoming a political talk. Okay.
Not so much. Yeah, I should probably stay.
Well, because I mean, usually when people talk while oil or petroleum is not kind of a good choice for energy, people start talking about the
Greenhouse
green gas, the
I was gonna link to that
warming,
eventually,
the global warming and stuff like that. But you find the political issues. Okay, good.
Well, we also have renewable energy, such as water, heat from the earth. Wind is really utilized one in countries, in states that there are a lot of wind, such as North Dakota that's got windmill farms. Oklahoma, all of western Oklahoma was full of windmill farms. My college, my undergrad where I went to, there were a lot of windmill farms outside, so that was a cool sight to see. Solar is where we're trying to lead up to, due to the fact that it's always there, except for at nighttime when it decides to go to sleep, like we do. Yeah. So we could also see a breakdown of the American usage. So petroleum is used the most, natural gas, but these are just percentages into a pie chart, if you like to see that stuff. And the current goal, we're trying to raise renewable energy higher than 11%, but the problem to that is renewable energy is sort of expensive-ish at the moment, and it's not really high conversion rates that we like to see, but it is being improved over time.
So what is the goal of this slide?
The goal of this slide, to talk about the types of energy that are out there and being utilized.
But I think this to lead us to the idea that we really need to work harder and better on solar energy resources, right?
Okay. Yeah.
But then probably you need to clearly,
Move
again,
on quick.
it's not, right now it was just general information,
Okay.
but you should really end up each slide with something really related to the next slide, to your final destiny,
Mhm.
right?
Yeah.
Somewhere in the middle,
Like
where you really
micro conclusions.
micro conclusion for a specific slide, or
Okay.
just leading to the main taken home message from this slide, right? And I guess this is what Japet was
Yeah.
also. What is your micro conclusion?
We want to see an increase of 0.8% used by Americans, or globally, in that case, not just Americans. Try to see that higher up to cases such as petroleum, natural gas, we're about a third.
But then, I would say you put open question. Showing this data, it looks like we definitely much better doing with wind right now, right?
Mhm.
And even with what is it?
hydropower or water dams.
Oh,
and
just
stuff
water,
like that.
yeah. And even biomass is a green technology kind of petroleum is, or not petroleum, how we call it, is definitely much more advanced, in a much more advanced state rather than solar energy.
Mhm.
So then your reason is that you want to focus on this because it's so less advanced, or because it really provides much more advances. If we can make it work, then it would be much better solution rather than wind, rather than water and so on.
That's exactly what my next slide.
Okay.
is gonna talk about.
Then again, lead us to this next one.
Okay.
So no one will stay with this question. You finish it, so it would be a very natural conclusion. Maybe say, well, you see, this is the smallest so far. Like this area is the least advanced so far, right?
Yeah.
While it really provides a great benefits. And the next slide will explain why it provides a great benefits comparing to the other solutions, right?
Yes.
Okay.
So the reason why we want to use solar power is due to the fact that normally, due to tidal waves, there are 0.3 terawatts available of energy, while for geothermal, it's about a maximum of 2 terawatts available, where hydro power is 3 to 4 terawatts availability. Biomass is maximum of 6, where we have wind at about availability of 70 terawatts. And we have the big picture right there where solar power, there's 23,000 terawatts compared, so almost over 1,000% of energy available compared to the already more powerful methods that are available. Yeah.
What is,
Is this per year?
yes.
Yes, per year. There you go. That's sorry. That was the next one where I was gonna say globally, the world about 18.5 terawatts per year availability. So being able to harvest over that will be beneficial.
So then I have a question. If you have a 25 to 70 available in wind, it should enough to get your world energy consumption 18.5. Why we need to bother about all other things?
Because wind conversion isn't the greatest at the moment either. It's
But
still being worked on.
wouldn't mechanics and fluid dynamics easily increase the availability of that power compared to years of research in developing solar panels, the materials, and all of those? Right? So you could more readily make wind now than solar. The thing that's important is 18.5. Do you think 18.5 is going to stay there
There
for
is-
long?
You can find in the Google, this is current usage, right?
Yes,
years ago.
it's 3 years ago.
Oh,
Sorry, I couldn't find
even
the
not current. So, but you probably can, it's better to find in the Google, it's showing the sketch, how it grows, and estimate how it will continue growing. And it's exponential growth.
It looks like
I was gonna link up to the next.
Then it's a question, answer to your question, right? So, to your question. So this data, if you return back to your previous slide, this 18 or whatever units, which is in 2015, in 10 years will grow probably 10 times. And then your wind power will be not able to overcome this problem, right?
So yes, so
Yeah,
China
and
is
this is-
currently doing a
It's only
much
for China?
better. Yeah. So PR China, I think I don't know what the PR stands
People's
for.
Republic.
People's Republic of
Yes,
China.
People Republic of
public
China.
relations.
As you can see, they're
I
doing
don't see blue.
it's really thin. That's the Americans. We don't really care about it
It's
'cause
more like Malaysia, is a green one.
oh,
Oh, it's very close to the green, okay.
Yeah. So yeah, that's like I said, Americans we love oil because I don't know. It's just
Wait.
No, this is
What is here? It's production of
annual production of gigawatts of solar energy.
solar.
Yeah.
Oh,
Solar.
You
yeah,
need
yeah.
title. It's not clear.
Oh, sorry about that.
So I was surprised when Malaysia put it using.
Yeah, this was from the Journal of Photovoltaics, so I forgot to assume that it doesn't say solar energy. But
Make
yeah,
sure you reference the other slides as well.
yes, I forgot to do that as well. So yeah, China's doing a really great job of annually over time increasing solar energy due to the fact it's renewable, it's that much cheaper. As you can see, for the rest of the world, they're also doing a job of trying to increase the fact of how much solar energy they are harvesting. And basically every country except for us, except for Europe, where they decided to take a little dip as well, but not by much. But essentially, the whole point to this is China. They're trying to be one of the leaders in developing this approach where we want to harvest as much solar energy as possible.
I'm confused. I don't know how to read this chart. Can you just give example, like what exactly this annual production?
Gigawatts. Okay, so
Like why China is better than? They're all changing pretty much in the same rate, right? I don't see what is special about this data on China.
Well, the fact that they're just over time, they're trying to harvest more and more. They're trying to be more efficient in solar harvesting.
Harvest what? Harvest of
solar
what?
energy.
So I think the y-axis is the amount of energy they get from solar each year,
Yeah,
Yeah.
and China's increased by like
they're focusing on harvesting.
3-4 folds. Yeah.
40 gigawatts.
Is China's increase proportional to everybody else's increase?
Then the data, let's say the blue, for example, Europe, how should I read this? I need to take the value corresponding to the maximum of blue and subtract the black? Or I need to add blue to the top of the black?
How you
Like Europe means only this blue?
Yeah.
Or it's a part which is covered by black as well?
No, Europe is just this much.
The difference.
Yeah, so overall, that's how much the world harvested in, about 21 gigawatts.
I see.
With China being the leader of the 21, then half of that energy themselves.
Okay, now it makes sense. Okay.
I'm sorry.
Because I thought, because usually again you need to explain clearly how to read this chart, or maybe put some notes in your slide. Because usually people just think pink, and then wherever your colors is just covering one each other. Then actually America is better than China in this, if you read it as adding rather than subtracting, right?
No, yeah, it didn't make sense that it's a total. That's a total, and then they're fractions.
Fraction for each, yeah.
Yeah.
Okay.
So why you think it doesn't change in the USA consumption, but China is doing better? Is it technological problem or issue?
It goes back to, I didn't really include this. There are Chinese solar cells companies. They bought contracts to where that's just their job. They're giant solar cell companies. They're much
Okay.
bigger over there because this is the approach they're adopting.
It doesn't necessarily they're making new technology or they're investing in technology.
They're just investing into this technology. Yes, more and more. They're trying
So
to.
the government supporting this area, right? Both in terms of technology, science, and engineering.
So I guess there is money in this field, and China's just the lead they're the lead investors in this type of technology. Are there any more questions on this?
I guess how does that tie into your last slide?
How do I tie it? Just trying to say that there are people looking for this type of technology. Well, not in this people, countries are looking for this, because as you can see, the pink tabs too, that's the rest of the world. It's not just China. They're also increasing exponentially a lot more than the Americans are. And Europe's been on a slight decrease, but I can't really explain for that. It's probably just because Greece is kind of holding the Europeans down.
Malaysia is
Yeah, I would just stick with saying that the tides of the peaks are changing and not focus on by countries. Because you can see that over the last like 8 years, there's an order of magnitude increase in the output.
Okay, thank you for that comment.
And it might not be exponential. It looks more.
No, this is a different thing. I was talking about usage of energy.
Yeah, this is
And
not
this is not
usage
usage of energy, this is production of
Yeah,
solar
but
power.
he said this is exponentially growing,
No, it's
and
not.
it doesn't look exponential.
No. My comment previously
Yeah,
was
I wasn't.
that again, if you return back to your previous slide. So this is not really answering the question which was on previous slide, right? So this 8.5 watts or whatever per year, right? So again, if you see the estimates of the total power needed by the world, or by America, doesn't matter, you probably can focus just on America, you will see that estimated in 10 years it will be growing orders of magnitude. So then being in this 23,000s rather than tens, right? 20s, 30s, 70s. is really much more reasonable goal rather than being a technology which not allows you to go beyond 100 terawatts.
Well, I guess being able to talk about, going back to Levi's question about the wind, wouldn't having a lot more windmills to take up land from developments as well?
But solar cells also taking land, right?
Essentially, yes.
And windmills, you only need a base, and you can grow crop around the base. Where solar cells, if you have solar cell, you're not growing crop underneath. They won't get any light.
But you can put it in the cities.
In
You can
slide,
put it on the-
Yes.
Do hydroponics with the solar cells.
in
eventually
slide
too.
2, you listed 2.4% power coming from wind, and now you're showing we have an overwhelming wind.
No,
power.
that's potential.
That's just potential. Yeah, that's global energy potential. Sorry.
But again, it
So
looks
that's
like,
not extractable, maybe, right?
but this is all limited, right?
Yeah, it's not. It's how much there is available, but not how much is actually.
Extractable,
It's how much is
yeah.
being produced. That's how much. That's where that 2.3 is coming from. Oh. So there's this cell. When I was mentioning, I guess that little video doesn't do too job. One of the goals of perovskites is right there on this side where the red oval's at is the growth of perovskites. So as you can see, it's been a steady incline, a huge increase compared to many other technologies when they first came out. So comparing that, you can see hopefully we're looking at higher percentages where when it first came out, it was turned out to be about less than around 13% conversion rate, where right now currently it's sitting at 22.1 when this was taken in about 2017. Where one of the main goals to perovskites is trying to reach the point where this blue circular line, where it says Sanyo, Panasonic, these are silicone cells. These are currently the cheapest ones on the market at the moment. Perovskites have a future where they can reach that point to where they are equally as cheap and reach higher conversion rates that silicone offers today. So that's technically one of the goals and game goals. Perovskites is trying to hopefully reach the point that silicone cells are at today. Any questions on this?
The question is that no one can read what exactly this table tells you. It's too many information.
Okay.
Too small.
So maybe you may want to
Zoom in.
Just a little fragment that you are showing so that it occupies the whole screen.
Okay. Yeah. So I'm sorry for this. Yeah.
I have a question on the previous one. So you kind of said, but why are you focusing on the red line when I see a bunch of other things above it?
Oh, so these are really expensive cells. They're more for military use because they use a lot of rare metals. So for everyday practical use for humans, for civilians, I don't think it would be a current thing. These are more for like latest military technologies that we're probably not gonna get our hands to anytime soon. We might get it eventually if they do find a way how to make rare metals not rare, but that's besides the point.
So you said silicon. Where's silicon on this?
Blue, right?
Silicone is right here. So silicone currently has 25.6% efficiency.
Another way how you can do it again with PowerPoint, you use PowerPoint, right?
Yes.
So you can really make this kind of circles and say extremely expensive.
Extremely expensive. Yes.
Something like moderate.
I'm sure I'll get the same question that gets. What about those?
Moderate price versus efficiency, right? And you can, and then like your highlighted red one is making sense as well, right? When you explain it.
Mm-hmm.
And then people probably don't need to worry about all the small details because you really point, you focus, you attract their focus to the main kind of features here. And what about the green, by the way, since we talk about it? What is it?
The green, cadmium.
Oh, it's a quantum
tellurium.
dot.
Yeah.
Thin film.
Okay, so it's in a kind of nanomaterials.
Where's the conjugated polymers? Because some people
Oh, they are
in the
probably
next
very low.
attendees of your seminar could be involved in conjugated polymers, organic photovoltaic.
They're not
Where
reaching
are they?
15%. They're in the bottom.
What about the gallium arsenide type things? No, why you're
It's
not
probably also
possible?
goes to the quantum dot nanotechnology, right?
No, that's close to 30% something like that.
So you say conjugated polymers?
There are no, because it should be
No,
19%.
the red circles on the bottom.
Organic cells, various types.
Organic cells raised. So yeah, low efficiencies, less than 12%. I don't know how cheap they are.
And it's kind of constantly not changing
Yes,
for many years.
well, if you can see this flat line right here where it just like died, I guess they found something right there, but it probably was just a cheaper method.
So I know
So the
that
system-
there are organic cells that are cheaper than all of these.
But efficiency is
The
low.
efficiency is trash,
Yeah.
but the electricity cost is lower than, I think, even coal.
cheaper. Cool.
But that's also not commercial yet.
Oh, the cells you were talking about?
Yeah, the cells that I'm talking about are not commercial yet.
Oh, because it's many factors you need to consider, right? It's price for the manufacturing, it's price for providing 1 watt per
Yes.
whatever, right? And it's price for, not the price, stability,
Yes.
how long it holds, and probably some other factors as well. Well, of course, the ecology, I mean, green approach and so on, so on.
Can solar cell have 100% efficiency?
Can solar cell have 100% efficiency? That's a question. In theory, we'd like to, but we haven't found or adopted a method to find 100% efficiency.
The question is why?
Is it possible?
Why have we not been able to? Lack of technology,
Who are Shockley and Quasar?
or Shockley and Quasar? People I've not heard of.
So, would you agree that they did discover that the efficiency of solar cell cannot exceed some very humble limit of about 35%?
They cannot achieve 100% efficiency.
Why? Okay, I will put it in a different way. Why and how the energy is lost in your solar cells? Why we have losses?
Thermalization.
And a little bit more than what do you mean by this?
So usually whenever you charge a material, it gets excited, right? An electron goes from
You not
The charge. You mean
charge,
excite.
you excite
Yeah.
first.
okay charges. They
You
It's not a
create
charge.
the, you create the charge pair, elephant hole pair.
Okay. And well, when that happens, the charge moves, and well,
And this is your current. This is exactly with the purpose.
so a current is created, and well, with anything that moves, there's heat involved. So heat will always reach a equilibrium over time, right? And I guess that's just how the energy is lost. Correct.
So you're losing energy after creating current or before that?
After, because it has to move, right? No.
So
probably
when you
lose
do
it before.
when you do your dynamics, you excite, then what happens?
It will relax.
Relax to
Low
the
energy.
ground state
the
Yeah.
bandage,
of bandage.
right?
Yeah.
And then once that's done, it can be removed to your anode and cathode, right?
Mm-hmm.
And then it will couple, right?
Yeah.
So when it relaxes the homolumo, or whatever you want to call it, what has it already done?
It's excited. It's giving off its.
So it's
Can you
released
just show
energy.
schematically again? We talk about the energy loss, right?
Yes.
So just show the energy you start and the energy which you end up at the level when it's coming as a current, as a motion of free electrons. So you have your material which is absorbing energy, right?
Mm-hmm.
And shows a schematic kind of where you really have this excitation, what's
And
the
if-
energy of this
If you want, you
excitation.
can draw right on the screen.
Oh. Yeah.
Oh yeah. Can we see them?
Yeah.
So
Ah, here, okay.
normally, right here, we have an electron or a charge. It'll go to, let's just say that energy level. So after over time, it'll just relax to here.
So now you're getting less energy.
Yeah. So over.
So this difference is already goes to just heat. Yeah, because this thermalized to the lowest unoccupied
lowest
state.
yeah.
This is where it can kind of move to your anode, cathode, or whatever you call it, the LEDs, and finally goes to the current, right? But now you have much less energy already comparing to what was provided as initial excitation.
Yeah.
And this difference just goes to heat, to the vibrational motion.
Vibration.
So atom starts vibrate quicker. The atoms get this nuclei get this energy, start move quicker, which means you just make them being hotter. Right?
Yeah.
You have higher velocity. Velocity, kinetic energy is related to the temperature. So you increase the temperature of your device, nothing else. So you lose this energy, or some portion of that energy. Instead of putting all this energy to the current, you put maybe 2/3, 1/3. The best probably you're showing right now is half of this energy goes to the current, right?
Yes. So
And again, yeah, the reason is thermalization, what you call, or just dissipation to the vibrational motion of nuclei.
So I guess vibrational motion. Can you relate that to non-adiabatic coupling?
Actually, you should.
You should. Yeah, because that's a definition of non-adiabatic coupling, right? Just
Yeah,
vibrational
because if
coupling.
electrons will be completely independent from nuclei and not really feeling how these guys move, right? Then of course this efficiency would be much easier to reach 100%. But in real systems they do couple.
Or yeah.
And that's why
Basically,
they
it's-
share this energy between, right? And you have this losses to the thermalization, to the heating.
Okay.
So then how do we get systems that almost have 50% if Dimitri already said that it is limited to around 35%?
That's a good question, but I don't know if civilians are allowed to military technology.
It's not,
Right away to-
it's not military, like, it's not classical.
I thought it would be. I
No,
guess I didn't really look into that. That's a good question.
it says on your slide.
So look on the name, there are Boeing,
Boeing.
and NRE, military organization.
Well,
Right, it says 3 junction, 2 junction, 4
It's
junction,
because junction,
right?
it could just be because of multi-junction.
So you
cells.
provide, like this electron, instead of getting to the low state
Yeah.
in one material, provided a very beneficial conditions to jump to the pretty much the same energy level with not really losing its energy to the another type of material and then another type of material. And this is how you kind of, trick your system, not really losing these two vibrations. You really go to the electronic couplings between two different materials, avoiding interaction with atoms, with nuclei, at some level. Of course, you cannot avoid it completely to 100%. This actually helps to increase the efficiency. Again, the main point is to avoid this interaction with vibrations and kind of isolate your electronic degrees of freedom from vibrational degrees of freedom. Whatever the means can be used. And like this multi-level technology probably is one of the way how you can do it, but on the other hand, it's very expensive.
So I guess like how you said about trying to reduce the degrees of freedom, is that how quantum dots work? By
Reduce the
being
degrees
able-
of freedom for vibrations, of course. You don't want to reduce number of electrons or number of holes.
Okay, yeah.
Your carriers, your electronic degrees of freedom actually has to be increased, right? You probably want to increase the carriers and their motion
So
to have a higher current.
I was I guess wondering, are these multi-junction cells I guess types of quantum dots? Because I know with quantum dots you can
In quantum
be
dots,
specific and
in
choose-
quantum dots, there is another way how you can improve this, right? What is it?
Well,
You have heard the talk when it was on Tuesday.
Does it have to? Well, my knowledge of quantum dots is you can easily try to tune quantum dots to try to choose specific band gaps that you want, and I guess probably missed that key topic too. That I didn't really. I guess I don't really know.
He was mainly talking about the increase or improving the carrier multiplication processes or generation outcomes.
Multi-accident generation?
MEG, multi-exciton generation.
Oh, yeah, I wrote that down in my notebook with a question mark. I was supposed to look it up later, but I didn't.
Look it up.
Yeah. So, yeah, I do have the note on that.
So the idea is again that you create you excite much higher energy, right?
Mm-hmm.
And then this energy again is not lost to vibrations, but it goes to another electron hole pair. And you kind of excite another electron hole pair with twice less energy, but now you have two carriers with twice less energy. Which is again, you're not losing anything in that case. But efficiency of the processes is still not 100%, and they were able to go to 44, I think in his slide was. With carrier multiplication, you were able to go theoretically 42, 44, something like this.
44 for a single junction, and 66 if you have two junctions.
66%.
And it.
But again, theoretical limit.
Yeah.
In reality, technology is still
here,
not there yet.
Here they say 4 junction, and it goes to some limit, but it would never get to 100%. Because he also said that you lose efficiency when you have to go through materials, right?
Oh, that's how they usually are all layered, right?
Yeah, but you still lose efficiency
A little.
through layers.
You never can reach 100%.
No.
That's the key point. Never reach 100%.
Yeah.
But the goal is to be as close as possible.
Mm-hmm. Of course. Yes.
So how does efficiency vary with temperature, internal temperature?
How does efficiency vary with internal temperature? Wouldn't that also have to, I guess, take place with like the materials resistance to, well, not resistance, but acceptance with the temperature, because most solar cells try to work at room temperature, or well, I guess most of these are done in a lab where room temperature is probably the ideal temperature.
But what if you cooled it down to sub-Kelvin?
Cool it down sub-Kelvin. Wouldn't that just...
He's asking, would it be better to cool it to the helium temperatures, or was it better to heat it to the temperatures of, I don't know, surface temperature of the star?
Then the device will just melt. It will not perform. It's sure.
I guess that would be the reason for the extreme temperatures of heat, or the temperatures of cold. Wouldn't that just make charges move a lot more slower? So you'd be able to, I guess, trap charges if they were slower, or they just probably wouldn't move at all.
So how would your non-adiabatic couplings change with temperature? Would they get bigger or smaller with increased temperature?
With increased temperature, they should get bigger, or the material just simply break apart.
So if you have more non-adiabatic coupling, is that going to help your solar cell efficiency?
I think it should reduce solar cell efficiency because of larger non-adiabatic coupling. Yeah.
So we conclude the higher temperature will reduce efficiency?
Yes, it will reduce it because of the higher non-adiabatic coupling constants. Oh, the constant for non-adiabatic coupling should be higher.
So you think that at lower temperature it should be more efficient?
Yes, if the device will work at that temperature, I guess. Yeah.
Is that what you wanted to hear?
Any more questions?
But honestly, this slide might generate a huge discussion. And you really putting yourself in a situation to have many, many questions. If people want to ask questions, this is the easiest slide to ask a lot of questions.
But then
it's a perfect slide then.
Time is...
If you want, no, they might ask after he's done with his presentation.
But everyone wants to go to the dinner, so people will not sit longer.
Yes, but he's also being graded.
I mean,
so if they ask a question and he can't answer it, then that might affect its grade.
Well, I mean, on Monday, Sierra's questions took as long as as the session did. So,
but again, it's no why, because her talk was too short. She
No,
was
but-
done like in 40 minutes or even less.
That's
than 40
how long it
minutes.
took to do it.
Well, but she was like I say, her time was really extremely short.
Longer, then you would less.
I think it was just they were very interested in the topic.
I think so too, because I think Olivia's was 40
The
minutes.
biochemists were.
Honestly, I don't think they were very much interested. They just felt that there were some holes there.
Yeah, maybe.
So, good discussion. I appreciate it. So sorry for this slide, but it's gonna be more polished, I promise. But so there's two types of applications we have: photovoltaics and LEDs, which stand for light emitting diodes. So how photovoltaics works is H bar or Planck's constant, omega.
What?
H
Oh.
H bar omega. Okay.
Okay, so photon energy.
Yes. So I was leading to. You scared me for a second. I thought I said something wrong.
No, I think we were both thinking.
Because you have H plus there.
Oh, that's whole. I'm
Yeah.
sorry. Yeah. And like I said, it's work in progress. It'll be more polished. It's just I wanted your comments on this. If this is a good approach for this. So, well, photovoltaics. How that works is we get light, excite material, where we separate the charge from hole and electron, and with that separation of charge, we're able to recombine and continue.
Recombined where?
Recombine where
Or you combine what?
No, he told charges would be able to recombine.
Which charges? Plus and minus?
Uh,
Electron and hole recombination, or which one you talking about?
with
When the current goes through a
Yeah.
circuit.
Yes,
Combined
that's
circuit.
he's expected to answer this.
yeah, recombine circuit. So current. Well, I mean, no,
What is your yellow there?
yellow for here.
Just read it. Yeah.
Continue. Yeah.
Continue.
Maybe contacts?
LEDs.
Contacts.
Contact LEDs.
Okay. And what on the other side then? Do you should you have a contact on the other side as well?
Yes. I guess the PV and LED was covering that, but yes, it should also have that. It'll be more polished.
So you should have both contacts, right? But one will be kind of going to the negative charge particles, and the other ones for your holes. And of course, the potential, you should have a difference in the potential between plus and minus charges. So when they connected together, then you will have a closed circle, and there is a current.
Yeah. Okay. Close circle and current. Yeah.
No, circuit.
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 What is circuit?
Circuit.
Just in case.
Circuit. Circuit is just a continuation of a thing. So like, say you have Game Boy with batteries. That is a circuit. The batteries are working because the electricity would just keep running around. Or yes, the
So
energy.
same here, circuit.
Yeah.
Metal. Short circuit.
Yeah.
Yeah.
So I guess how batteries work in battery operated devices. That's a circuit.
Can solar cell be considered as a battery?
Yes.
Okay.
Considered a battery.
Can it be?
Well, it's not a battery, but it's functions same way as gives
So the only difference
Okay.
that your
potential difference and then
your
Okay.
battery is creating energy
Chemical potential.
from chemical reaction, and this guy from sun.
Yes.
You need here's
But
the
it's,
potential
but a
difference.
solar
Energy of
cell
cell
does
in-
not inherently store energy, where a battery does store energy.
This is true.
you're correct in tiny details, but from bird's view,
Okay.
So that's just how a photovoltaic cell will work. It will recombine. The circuit will recombine, or the charge will recombine with the said circuit, and continue forever and ever until the device is weak.
I don't think we call it recombine. This is not the right language to use. Just continue to the circuit,
Okay.
to the contact, either with this potential or that potential.
Okay. Yeah.
Because
Thank you.
there is another problem that technically, even if you have your separation of charges,
Mhm.
they steal like your electron might return back and takes the place of hole. And this is what we call electron-hole recombination.
Okay.
And of course, then you're losing your carriers. This is a bad process, but it's still there. It can happen. So it's another thing why you need to think about. First of all, you want your charges to be separated, and electron from holes, right? You want them electrons go one way, one contact, holes should go to the other contact, right?
Yeah.
And you don't want them to recombine, kind of return back to the ground state. Doesn't matter when they do it. In your initial material where you excite, or they can even recombine when electron is already moving to the other material, but your hole stays in the same material and they still can recombine. This is still a bad process. I would avoid the word recombination.
This is undesired processes
Yes.
that need to be avoided.
Yes.
And he's
But
presenting an idealized situation on the zeros.
I just suggest you don't need to go to these details. I just suggest don't use the word recombine, because again, usually recombination means something not helping. Usually people use it in a way of whole electron-hole recombination. So just say that it just continues moving to the contact, something like that.
Okay, thank you. So yes, so that's how photovoltaic cells work. And there's another type of application, the light emitting diodes. These are usually found in TVs, lights everywhere around us.
Actually, I have a question. D stands for device or for the diodes?
Diodes, sorry.
Diodes,
Light
really?
emitting
No,
diodes.
you said diodes.
No,
You
it
said
is
correctly.
for diode.
For sure, right? It's not
LED is
device. It's
diode.
Okay.
Yeah, sorry. So
Why not triode? It can be used as a triode as well.
You do not need the third electron to emit light.
No? Okay.
So, little phenomena to get an LED going on, it's considered a trap state. So, how I
Wait. Before
Wait,
trap
don't-
state, just tell us what is light emitting diode. Before.
Oh.
I can give you the hint. It's exactly the same as you just discussed, just opposite.
you charge or you excite.
No.
Or you inject.
Your goal is now to get excitation as your output. Here, your excitation was as input.
Okay.
Now you want it to be output. Light should be
Oh, yeah,
excited
I mean, it's
as
not-
your final destiny, right?
Yeah.
But for this, you actually apply the current. You already already have your free electrons, right?
Mhm.
Which kind of move now to your material. But here, your goal was to create these free electrons.
So I guess in
Can you make a demonstration of light emitting diode while you are speaking?
make demonstration of it. So what do you mean by that? Like
Any of our flashes are light emitting diodes.
Yeah, I thought I said at the beginning whenever TVs are usually LED or your TVs
Yes.
I mean, the lights over our heads.
Most of yes.
Most people's computers they're pretty much looking at their cell phones by this point. They're all staring at something.
Hopefully not by the third, fourth slide.
Hopefully. Some people usually do by the introduction.
This is a good way to attract their attention.
So
Just
there are
guys who are looking on your phones, by the way, your phones work because.
yeah, that's a good way to put it. As you said, there are free electrons that.
No, you apply current in this case.
Oh, we apply.
And current is the motion of the electrons.
Inject charge carriers.
Inject charge carriers, where the material then get excited, but how LEDs work is the charge will be trapped and not really recombined back with the circuit. So that's usually done by trap states. And
So you're
Wait,
saying
wait.
yeah.
You're going into details without telling the main thing. Right now, your charges that you have injected will recombine via radiative process.
radiative process, yes.
So they will recombine via emission of light.
Okay.
You end up having electron in your unoccupied state and hole in the occupied state of this material, which is in a red circle, right?
Mm-hmm.
And on your diagram.
But this is excited state. No one wants to be in excited state. So then what happens with this electron in hole?
In the excited state,
They want to go to the ground state. How
Yeah.
they do it?
Emitting light or
So
radiative
electron
emission.
returns back, kind of taking the place of hole. And if the material already has a property that the low state are optically active, means they really can emit light. They have non-zero transition dipole moment for these states. Then it will goes down, low in its energy, and this difference in energy goes as a light, as energy of the electromagnetic wave, of wherever this red, infrared, blue, ultraviolet, wherever your energy gap is allowing.
Where does wavy red arrow with a label h bar omega,
Where's it going to?
It going down.
is it going inside or outside of your device?
It is going outside.
In the light emitting diode.
Yes.
And where it goes inside or outside in the photovoltaic device?
It goes inside.
So that's the difference.
And again, this is your kind of input. You need to shine light first to get the current in the photovoltaic devices, and he's completely backward processes. You first apply electricity, right? The current, and force your material to shine light.
Okay. Forces shine light. Yeah, I guess that's the whole point to light emitting diodes.
So do you need a trap state to emit light in an LED? Because you've said trap state
Or it's better
several
not to
times.
have it.
For the most part, it's not. It's better to not
Avoid
have it.
Avoid it, yeah.
Yes. That's basically the goal is to.
Then you should not talk about
Then
trap
don't say
states for
trap
this
state.
slide.
Should not talk about trap states at all. Okay.
So here you present idealized devices
Yeah.
without parasitic processes.
But for like Aaron, he does magnesium dope, which is a trap state, which is needed.
It's a
for-
different.
Not
It's not a trap
It
state.
is
It's a intermediate
intentionally
state.
created.
It's same like in
something.
a laser. You would not call it a trap state.
Yes.
You specifically
Like in a
dope.
Ruby laser.
You
this
dope
dope.
your material with like chromium ions and so on, right, to create the intermediate long-living state. It's not a trap state. It's a different story. It's
Yeah.
actually emitting. It's highly emitting state with a very long lifetime. Yeah.
The word trap has negative connotation.
Very bad.
So, yeah.
So what does the def mean?
Non-relevant. It's just
Okay.
a picture of my phone that I took.
Okay, so this is like a snapshot.
Should it be
of
like
more stuff.
definition?
Yes, it should.
Okay.
That's what it stood for at first. I was trying to define
Okay.
photovoltaics and LED. Well, the applications. Yeah.
You can find a lot of these diagrams online, by the way.
Yeah, this is kind of a last minute
Yeah.
added addition to my slide. I
But-
apologize.
But on the other hand, it's confusing, and I would suggest probably you can focus your talk just on the photovoltaic applications. And again, even if it's related to his PhD, it doesn't mean that it has to be exactly on the point to his PhD. Because otherwise it's making really confusion. So then all your previous presentation was about photovoltaics. It's clearly connected because it's completely reverse processes. But my understanding is that suddenly you start talking about light emitting diodes after that slide, then it really kills all your.
So
Then the question is why I need to know about
The
photovoltaics.
suggestion is that there is a lack of connection between previous story and this story.
I don't know. If you continue talking about photovoltaics, I have no problems. Then I just will say, well, I really don't need to know about light emitting diodes so much. If you continue to talk about light emitting diodes, then I would say, what was the whole story about the photovoltaics then? Why not to start with light emitting diodes right away?
Or if you really want to show both of them, you need to give a little warning at the very beginning. So I will show you two major applications, compare them one versus another, and then lean towards one of them in more detail.
Okay. Yeah. So, yeah.
But we are in a slide number what?
6.
Number
5.
6. So even if you spend about 1 or 10, well, suppose 2 minutes, it's already your 10 minutes of your 40 minutes talk should be 40 minutes
I
total?
think like 40, 45.
Okay, so it's already 1/4 of your talk, and we still don't know what exactly you are going. Like, what it still looks like it's. We don't know where you like. It looks like you were talking about photovoltaics, talking about perovskite, saying that it has a great future, great promise.
Yeah. Smart organization wrong.
But it's probably really time right now, maybe next or in. But I know that I see your slides. I know that there is no any question address, like any slide addressing my question.
Yeah.
So maybe tell me what exactly your goal in this talk, what exactly you're going to present in this talk as your main subject, as your main question. Before it was background, right? You already presented all this background, so what? Then,
So,
where are you going to lead me next?
perovskite is a new photovoltaic material.
You already showed it.
Wait.
No. You already have shown it in your previous. Go to the previous slide. Previous slide. This one with a red kind of color, right? You're saying that perovskites are increasing their efficiency very rapidly, and they have a very great promise in terms of quality, quantity, blah blah blah, right? You kind of already give us the idea that you are going to talk about perovskites, but they already exist. Like this is the data of existing devices.
Okay.
Then, but it should be scientific talk. Then it means you should say what exactly is the challenge there. What is still not solved from scientific point of view? And it looks like it's not solved in the sense that we're still a little bit behind the blue and much less this 50% there. Then you probably need to say, well, they show good potentials that it's probably possible, but there are still some issues. Something is making it not done right now, and then maybe your talk will be about that, and then you say, well, here is the challenges which we have to overcome in these materials. Or maybe you're taking completely different paths, I don't know, but you need to say me what exactly is the next more detailed, more focused approach, and what is scientific in your talk will be next.
Okay.
Is there a similar table for efficiency of light emitting diodes?
Probably. I didn't really look into that. I just know. I've just known this type of chart since about 5 years ago.
But maybe I missed that. What was the title of your presentation?
It's a work in progress, but yeah, perovskites is the thing. Is the placeholder for it?
It will help us
So no
to go
title
to
yet.
your
No title yet.
talk.
It's just a placeholder more.
So when do you have to have your abstract and title in? Is it next?
I have my speech is on October 27th, so the week before. I should try to.
So that's
because
the
I think
20th. So you have about
because I think
15 days.
they sent out the abstract the day after.
2 weeks.
The person before.
Do you have
he does
something
it,
on your mind
or
now?
after. Huh?
Do you have something on your mind now? Something like maybe?
Well, before going to the talk, again,
We
tell
don't
me
have
what
any
you're going to
goals.
discuss after
Then,
that.
That's goals
we should go
question.
from there.
Because
Yeah.
if I understand, there are no words except a few in your next slides, and my understand. And again, I'm not going to go through your discussion of your results because this is not related to your second year presentation. So then it looks like all the information which you're showing after that slide is about light emitting diodes. So technically, you're having two talks in one. One is about photovoltaics, which again says, perovskites are good for photovoltaics. That's the only thing which I can learn so far for your 15 minutes of your introduction. And then suddenly you start talking about photovoltaics, saying, it's just opposite processes. So let's take perovskites for photovoltaics and make them good.
So
Do you see a problem with your logics?
yeah, I'm talking about two different applications in one talk, which isn't a good idea. Because
You to refocus my attention as a listener first, and second, I still don't know what exactly is the message you want to pass to me. What exactly I should learn from your talk so
Okay.
far.
So, I mean, what I want you to know is these have the potential to excel at both these applications. But I guess for the most part, I am talking about mainly one application, like you said. But
So what's holding them back from being better?
holding them back from being better,
It's like a general.
Not as good as other guys.
not as good. Due to the fact that other guys probably have had more substantial years of being worked on compared to perovskites are pretty much one of the newer ones, except for some of the more multi-junction
But
ones.
this is not scientific reason.
And
I mean,
you,
you cannot study this material just because of this reason and say, give me more money.
and the rate is a lot higher than all the others. So that would indicate that they don't need as much time. So we'll soon be at the theoretical limit.
Efficiency, yeah. Yeah, because I mean, well, I guess at this point right here, there was a little slight decline where it didn't increase as much, but then it's shot back.
But I
up
really
next
have a
week.
question. What exactly you want to talk about? You want to talk about the how to solve the problem of perovskites and photovoltaics, or how to solve the problem of, and what exactly is the problem of perovskite and in light emitting diodes? Which one?
I guess diodes is the one I want to try to solve. It's probably more money in that sector for.
I have a feeling that this is what your supervisor wants. But again, this second year seminar is not about what your supervisor wants, it's about what is your choice.
Mm-hmm.
You still have a freedom.
Yeah.
Because if you go to LEDs, all of the first 4 slides
Can
don't,
be,
don't
yeah.
relate to LEDs.
And again, even either with LED or either with these guys,
Yeah.
the question is what,
What is holding them back?
Erin question, what is really the main challenge in this field so far, which we really need to address as soon as possible to make them really in the top of this panel, or to be the best light emitting, and again, what exactly the problem with light emitting devices, the diodes is also, you didn't even touch yet, right?
Yeah.
So, okay, let's move to the light emitting diodes. What's the purpose? We have so many devices working already, the technology is there. Plus, we have organic, it's very different, like Dmitry says that, oh, shows the same efficiency for the light emitting diodes. It would be completely different story for organic light emitting diodes. They are really showing very great properties as light emitting diodes and have no any problems as they have for the photovoltaics. There are huge amount of materials which showing very good properties as emission properties, right? So then again, the question would be why perovskites?
Why perovskites? That's an excellent question.
So I have a question that will help relate to that. Do you know the maximum efficiency of an organic LED?
No, I haven't done my research on
Okay,
all of these stuff yet.
25%.
25%.
That's the max it can ever get to. Do you think it's 25% for perovskites?
I think it's like 28% for perovskites. It's theoretical.
No.
Do you happen to know it then, I guess?
So for that, it's almost 100. And the reason why I say that is for when you do electronic excitation,
Yeah.
it did not involve optical excitation rules, right? So for organic cells,
What are you talking cells?
yeah, LEDs.
It's not a cell.
Okay, sorry. For organic LEDs, right, it can excite into the singlet or triplet, right? How many triplet states are there compared to the singlet?
Isn't it roughly about the same? Oh, it's in the name itself, isn't it?
Yeah, so there's 3 triplet, 1 singlet, right?
Yeah.
So if you have 3 triplets, and now you excite to those, or spin flip emission, are those optically active?
Spin flips?
By the way, Levi, with internal quantum efficiency of organic light emitting devices, it's approaching 100%. So, you're 25% not really right according to the Wikipedia.
So, at least a year ago, they were saying that the maximum external efficiency is 25%, not internal.
Okay,
So
then again, we need to define what you call
That
efficiency.
could be going from singlet states, which singlet states, that's why TADF is so important.
Why you're talking about this one?
Because that's one reason why perovskites can be helpful, because they can reach almost 100%.
No, same for the quantum dots.
That too.
Then why not quantum dots?
Or quantum dots of perovskites.
Combine both. Yeah.
But,
That's a good question. Thank you.
right, so
Yeah.
you might be able to look at the reasons for like the
Perovskites.
difference, because absorption has to follow optical rules, where electrical excitation follows different sets of rules,
Okay.
right? And then that could lead you to answer Aaron's question of why this over what we currently have.
Thank you for that question. I actually cleared out a lot of answers myself too. That was a great question. Thank you. Thank you, Levi, too, for the explanation.
By the way, metal organic dyes are also called OLD.
Okay.
So, and
Then
there's not this problem, right?
Triplets emission is fine. Yes.
So, there's
But did he answer the question? I missed his
No.
answer.
He doesn't know yet.
I don't know yet.
But
so-
you help in. I thought you were saying something about band gap for the perovskites, no?
I didn't say anything about band gap.
Ah, okay. Then I will ask you, what is a band gap? Typical band gap energy for perovskites?
What is typical band gap? About 1.5 to 2 EV volts.
And in a spectral range, is it visible, infrared, near-infrared, UV?
Daniel, looking on your slides, your answer is on your next slide.
Oh yeah, that one.
Oh yeah.
So I guess it just depends on the color or the highlight anion that you decide to choose with your perovskite.
No, but this is for the quantum dots, right? Or for what?
Yeah. So
Oh,
Yeah, that's the quantum.
are there perovskites there as well?
Yeah, these are based on perovskites. Quantum dots.
Perovskites quantum dots.
Yeah, this is the paper that Aaron refers to a lot, so I've been told that he loves this paper.
And I think before you go, what is the band gap in the bulk materials? Yeah. Is it around 1 electron volt?
For the iodine ones, yeah, it's like
And
one.
for the other ones?
Can you finger
Like higher.
on this
Huh?
spectra?
Higher?
Yeah.
How much higher? But are they really
Wait.
close to the near-infrared? Can we call
The
them
answer
near-infrared?
is there. The answer is on the board. So, Daniel, can you explain what you are showing there?
So depending on what type of anion you use, you will get a different emission of light.
Okay, so there are a series of perovskite quantum dots with different anion. And then each series has a range of band gaps in a specific part of the spectrum.
Yeah.
Which one in this series, can you please finger the one with iodine? Just approach and show.
Yeah,
So which one of these three would correspond to larger quantum dot and approaching the bulk gap? To the red or to the blue?
for the bulk material? Or is that what you asked?
You do show cesium, lead, iodine 3.
Yeah.
There are 3 peaks.
Yes.
What is the difference between them?
So that's just dependent on what type of.
No, they all have iodine.
Okay, can you return back to this question and torture him for this? I just answered this question. It looks like if you just look on the bulk perovskites, their band gap is very close to the near-infrared. How many other materials we have which can, and they probably can emit light, right? How many other materials we know which can emit light being in the infrared range or near-infrared range? Really a few, right? So it looks like, because most of the organic molecules, they have band gap in the visible or even in UV, and much more in the UV rather than visible. But really having materials emitting in the red and especially infrared or near-infrared in between is really not many materials which can do it.
No.
And it looks like if you look on the bulk, it's already in this range. Then the question is, can we make it really be optically active? And can we tune the energy of emitting light, not only by, there's some tunability based on the cations. Well, this is what Dmitry was leading to with these cations, right? Lead versus
Or anions.
anions. Bromine versus chlorine. Okay, so cesium is not making the difference.
You see,
No,
it's,
It's just
Okay, so it's bromine and chlorine. Okay.
Yeah.
Well, I thought they go in a different concentrations, but maybe I'm wrong. Okay, so you can do it chemically through changes this anions, or you can just go to the nanostructures and change it, and then we know the confinement effect, particle in the box effect, changing it through the size as well. So, but the thing is that you already start with you can increase, go into the visible, right, or decrease the energy, go into the larger sizes and or in bromine, wherever. If you really want this tunability, but you already can start with something emitting in the red or infrared, near-infrared region.
Yeah.
This probably makes it much more unique comparing to organic, in addition to this problem of triplets, which again can be overcome with metal organic complexes, which also called organic, by the way. And this probably also might give it a little bit better ideas, or better approach than regular semiconducting quantum dots, although I'm not convinced 100%. You still can have random emitting semiconducting quantum dots, so why perovskites?
Daniel, can you finger on the panel D on your
Yeah.
finger?
Finger what?
Point.
Oh, this right here?
Yeah. What is written as a legend?
Photoluminescence? Or
Legend, not the axis, but legend.
Oh, quantum yield of 50 to 90%.
So how does it compare to quantum yield of other materials, and what is quantum yield?
So, it's
Quantum
quantum
yield of cadmium telluride nanorods is taken as a kind of measurement, as a reference for this type of materials. Everything is compared to the cadmium telluride nanorods, which is going to 100%.
But what is quantum yield?
the theoretical efficiency that you can get out of it. Suppose.
You need a formula.
I need a formula. That'll help. Yeah. Guess I didn't really think about that.
Written note. Formula for quantum efficiency.
Would it be kind of, if you just count number of photons which are shining out? Can you?
Can I? Not with my eye.
But in the lab,
In
you're
the
probably supposed to have some devices which can count.
Yes, that's what spectroscopy is for.
Exactly. Yeah. So technically, then the more photons it can eliminate, right? Per.
Emit.
I think it's emit over absorbed.
Over. It's not absorbed. It's emitting devices.
No. You excited or
Excited.
Right. That's what I'm saying. Like, depends
ratio. What's
per what? Per energy used to make this excitation, right?
Oh, it's what the band gap energy is, right? The energy it's used to excite.
Not really, because you also will have losses there. It's either the energy which coming from your current, wherever you are.
Okay.
You can estimate what would be the energy of whatever your difference in potential for providing it, or if you emit through the absorption, if you're not really involved, if it's not really light emitting diodes, if you just absorb and then emit, then it would be per energy absorbed.
So we are not going to return to previous slide and go forward?
Previous slide just has structure perovskite. I don't know if that deserves much lecture.
But again, it looks like your structure perovskite would be, if you go to the light emitting diodes, then your structure is important to explain how the chemical composition will affect the band gap of this material, right? Because again, you have two effects. You can chemically modify it, or you can do the confinement effect.
Okay.
Size.
Yeah.
Making it larger or smaller, which will tune your energy as well. And again, the simple explanation would be particle in a box idea.
So are you only going to talk about cesium, or are you also going to talk about whatever that ion is?
Which anion? The
I mean,
ammonium?
the methylammonium.
Yeah. I'll mention. It comes up in one of the papers. It's a common cation, so that's why.
Yeah, the only reason why I say it is if you're not going to say it at all, it would probably be better to replace it with cesium, because then the next slide is like, oh, how did cesium come up?
Oh, yeah. So these usually just the divalent metal, where common ones are lead as shown. Sometimes it's cesium or gallium. Gallium is a really common one as well. So yeah, that's usually what happens. Typically, the A organic cation tends to be methylammonium. X as any type of halide doesn't just need to be iodide. It's just
Yeah, I understand. I'm just saying, for when you do it for the department, it might be good to make it more concise so that someone doesn't say, what is that? And then you have to go into a 5-minute discussion on what it is.
Yeah, I hear you. Thank you. Thank you for the input. So is there any more questions on this slide, I'm guessing?
Did you explain this slide?
I thought we had it. Well,
Because we were on the previous, and then Dimitri said go a slide forward.
But maybe you had your own plans of what to tell about this slide.
well, normally it just, so you get a different type of emission depending on what type of ion you use. Typically, you'd want higher wavelength because it's a lower band gap to excite, but that's just ideal conditions. It doesn't always have to be it. So if you get it near the UV range, the band gap's just gonna be higher, but it doesn't mean that it'll just be worse than using a higher wavelength but lower energy excitation. So up there at the top right, we have the absorption over the photoluminescence. So as the wavelength tells you, it's just a trend that is followed from the absorption spectrum. And plot B has is stating that this material has a quantum yield average of predicted to be 50 to 90%, with this chart taking into effect that the recombination rate was about 29 nanoseconds, where most of the materials other than the iodide or this cesium lead triiodide, he is the one that relaxes the slowest compared to just the trichloride one, where that one's not included due to it not showing up at all because of the some effect with the fluoride. Sorry if I can't give you a better example. Explanation for that, I gotta reread that one again. But I know it's due to some effect with the chloride does in confinements. But yeah.
So if you had to use one of those for your solar cell, which ones would you use?
I'd like to try to use the triiodide one because if the emission is a higher wavelength, it's a lower energy to excite compared to something as near the UV range.
But then wouldn't your potential on your solar cell be relatively low?
The potential be low.
But then he will absorb the whole spectrum, like a funnel.
I think the general theory is that
Doesn't have the potential.
the optimal absorption is like around
What's that called?
like 700, 650 nanometer range. So like that's usually like the band gap that happens.
So you're saying that about here?
Yeah. So if you have an absorber material, that's usually where you want it to be.
Thank you.
You.
So here's a type of spectroscopy that's used to measure the what's it called? The radio recombination rates of perovskites. So this is a optical pump terahertz probe spectroscopy. So how it's done is it uses delta T over T. So the difference between these two pumps, or the probe and the pump, over time is used to it. So one of the pumps is shot through the perovskite film with the probe measuring the point of effect on the film. That is then shot out to the detector. It's all done in the terahertz range. So then with this, it's shot at a different phonon influences. So with this microjoules over centimeter squared.
Influences or fluences?
Fluences? Yeah, I kept saying fluences. I thought it was a typo influence because I've never heard of it being used fluence. Probably my English for that. I don't know, I was bugging out on that. So I didn't really know the point to this chart because I sort of figured if you shot something more energy, it start off much higher and delay over time. But this is just how they used to model radiative recombination. And
How we read this graph? I don't get it.
so each of these colors is a different amount of energy that was shot to it. So the area, it stays the same. It's just the intensity of the light is shot at different intensities. So 6 microjoules, 16 microjoules is almost 3 times as much, as more intense than that, then doubled, then almost tripled again. So it just gets relatively stronger, the light that's shot at.
So if I asked you an experimental question about this, could you explain it?
Could I explain?
Because the previous slide you show a diagram, and if Dr. Soon's there, that is what she does, or somewhat what she
Dr.
does.
Rogers will be there.
Dr. Rogers will ask you a question, so if you cannot explain it,
Yeah.
I wouldn't put it up.
Okay.
And it sounds like you might not be able to explain it because you said, I don't know why they do this. So make sure you know what you're putting up, otherwise you're gonna be there for 2 hours answering questions and you have no idea how to answer.
And before that, why do you need this slide and previous slide? Do you need these 2 slides for your talk?
Well,
I don't know, I'm just wondering. Yeah.
I guess it's more for a fact that I don't know why I showed the previous one, but it's probably I should probably just use this as a supplemental thing more than anything than an actual slide. But yeah, you're right on. I just included it because I guess if I include something, I kind of have to learn about it. So I've never heard of this type of spectroscopy before, so I thought it'd be interesting to try to learn it. But yeah, the only reason I wanted to learn it because is they were trying to, I guess I gotta read the paper a little bit better, but it's just how they used to model experimentally the recombination rates, or try to model the mechanism behind it. So I guess being able to model mechanism is kind of important since a lot of isn't that what pretty much organic chemistry is all about, trying to model mechanisms?
Different mechanism.
Yeah, it's a different type of mechanism, but yeah.
So why is non-radiative recombination important?
Why is non-radiative? Because well, non-radiative recombination is important because it doesn't involve exciting the material with sunlight. So we're just including it, just connecting a current to it will suffice.
So you're saying that if you connect your LED, it will start emitting light spontaneous without putting energy in it?
No, you would need energy, yes.
So then what is non-radiative relaxation?
So that basically just means that light won't emit.
Right, so you have radiative and non-radiative.
Yeah.
Which one's good?
Doesn't that one sort of then depend on what type of application you're trying to apply it to?
We're talking LEDs.
LEDs. So for LEDs, you kind of want radiative.
Yeah, and you want to suppress non-radiative.
Suppress non-radiative. Yes.
Because you're losing photons every time it recombines without emitting a photon, right? So I think you guys work on looking at non-radiative and radiative recombination and getting the ratio, right, Dimitri? You can do that? Yeah.
Okay.
So let's cooling.
Cool. Okay. You have a question for
I
Timmy?
have a question. So you are going to compare your computed results with the experimental ones?
Am I gonna compare? It's nice so you won't be trying to say that you're making up your results. It's good to try to compare to something that's
So
basically
in your seminar, are you supposed to present your research or?
No, so I guess I'm gonna cut that part out then. Talk about papers, I guess. Yeah. So there's also another study that they did with the same materials where they shot it at different types of intensities, where this red line is stating the exponential decay of mono radiative recombination or mononucleic recombination. So that's just what that red line is stating. I know there are probably some questions to that.
What is that term?
Maybe by single exponential.
Yeah, singular nucleic radiative recombination. Or
Just put text next time so that if you are not sure, it is written there.
okay, yeah, I had it in my notes, but that's okay. Sorry for that. Guess I need a little bit more work on that, or a lot. So here's just a summary of what they tried, or what the experiment does is just model the charge carrier mobility and the recombination rates. And what is found is usually the flat film of these materials are found to be much higher. Well, the charge carrier mobilities are found to be much higher than that of meso titanium oxide or mesophorous titanium oxide materials, meso aluminum oxide. But so that also goes back to where K1, K2 is for the mono radiative recombination, and the K2 is bimolecular recombination, where K3 is in just OJ recombination rates. So one thing that they're trying to state too is if the material is lighter, so such as methylammonium tin iodide, the charge carrier mobility should be much lower due to the fact that the material is much lighter. Where if we add much more heavier atoms like lead iodide, you see the charge carrier increase by a lot more. And that's sort of the takeaway point is that, well, for this experiment that they ran, they found out that the flat films are much better for charge carriers than these mesophorous materials.
What is a meso titanium dioxide? What's the difference in film architecture between the two?
The difference between the two, it's a different shape than the structure I showed earlier.
Different shape of what? Film of what?
Of solar cell. Or
So who is deposited to where?
was it deposited to where?
Yes, just explain what is in this table. So how your perovskites are designed in space? Are they just flying in the vacuum, or they're sitting on something?
They are.
So it's not a solution, not colloidal thing. So it's on some what?
Well, it's a bulk material, so they sit on top of each other.
No. Our world is not made only of perovskites. They're sitting on some other material, right?
Yeah.
So like you get electrodes, whole transfer material, electron transfer material. They are arranged in the form of sandwiches.
Sandwiches are layers.
Yes. So layers of what?
Layers of well, I guess they're ligands.
No. Ligands, but may or may not be there. But what is the substrate? You don't need to answer. You need to just point on part of your table.
I guess how they're made is
No, next, third column.
the architecture. So I guess
But what does meso mean?
meso doesn't meso just mean like the top of plane?
No, it's in Spanish for mesa caldera, for mountains, and meso is between bulk and nano.
It's in between both.
It's between it is bigger than nano but smaller than bulk.
Okay.
So it's an abbreviation for metaporous metal oxide.
No porous. Okay. Thank you. So here's also what they did with what they found out here was what happens when you cut a perovskite structure.
Daniel, I have an important question.
Yeah.
When before you were explaining engineering and experimental papers, is this about experimental paper as well, or is some what is it? What are you going
It's a
to present?
DFT study.
So it's calculation.
Mm-hmm. Theoretical.
So you need to announce it.
Okay. I need to announce it. So yes. So this is a theoretical approach at looking at what happens if you cut the perovskite at a different phase. So they had two models where they exposed primarily the lead and the iodide, compared to where they just had the organic cation being exposed to the surface. So it's just different types of surfaces. Well, then they took a PDOS of it. They found out that usually cutting the different surfaces didn't have too much of an effect. Well, it had an effect because the lead iodide rich system, the band gap was found out to be almost a half of EV smaller.
Wait. Are you expecting everyone in the audience know what is PDOS?
No.
So why do you go so quick?
So
Or put placeholder, like here I will explain what is PDOS.
okay. So the PDOS is stating what type of these are different types of ligands, different types of metals, different anions, and the PDOS states what each of how much contribution these are giving to the overall electronic structure. So you found out. So we see that the methyl ammonium and lead, they don't really give too much in the valence band, but they come up. Well, the methyl ammonium does not come up at all in the conduction band, on both structures, while the lead is silent on both the valence bands on both structures. Well, both different types of rich surfaces, but they come up really big in the valence band, or conduction band, I'm sorry. So you could say that lead is the primary contributor to this, so that's probably why you see there'd be a bigger contribution on the lead rich surface more than the methyl ammonium iodide rich surface. While for iodides, it's usually seems to be the same for both structures. So you can say that having a lead rich surface will give you more density in the valence band.
Could it be that the lead in the lead-rich surface is not well passivated, so it makes trap states, lowering the states from +2 down to 1?
That's a safe assumption. There are considered to be less trap states in a lead-rich surface.
There's less trap states in
Yeah.
one. So then it's opposite what I just said.
Yes, opposite what you said. So the band gaps also on the lead-rich surface is found out to be half an EV volt smaller than a methyl ammonium rich surface. So what that means is it's going to take less energy to excite a lead-rich surface than a methyl ammonium iodide rich surface. The tau D in femtoseconds stands for purity phasing time. you can find out that relatively it's the same thing, so I didn't include said chart. They found out to be much the same type of trend on both of them. Well, one of the key things that we should be looking at is the last two things, which NAC stands for non-adiabatic coupling, and that is found out to be almost tenfold bigger, but I'll show that on the next slide. So the tau in nanoseconds stands for the excited state population. So you see that the lead-rich surface is also populated a lot more than the methylammonium iodide-rich surface by almost 8 times. So the charts are given right here, where you find out the population of the lead-rich surface is bigger. I don't know, I just repeated myself on that, but yeah. So what that means is whenever you excite the lead-rich surface, there's tends to be more charges that get excited compared to the methylammonium iodide-rich surface, which is kind of a good thing.
So is there a reason why it's kind of periodic in the decay?
Well, it's periodic in the decay, is there a reason? It could just probably be due to the fact that
It doesn't matter. I just asked that out of curiosity. I didn't know if they mentioned that in the paper.
yeah, I'll look into that. I'm pretty sure they talked about it. Yes.
How do you come up with the P dots from the dots?
How do you come up with P dots from the dots? Don't you just take the contributions from each atom? You take the contributions from each atom and their local density, and then you just add them up on wherever they're found, whether it's in the valence band or conduction band.
How do you partition?
How do you partition?
Maybe that's a better question. Because the orbital can be spread out a bunch of different atoms, right?
Uh-huh.
Where do you draw the line?
That's a good question. Guess that's something I need to look into a lot better. How to get PDOS. I haven't done that personally myself, but I should probably get familiar with that. Thank you, though. Yeah.
What exactly do you mean by the dashed red lines on the figures on the right?
A linear fit. It's just a trend line. Or, yeah, that's fit line.
Why are there times there instead of like a slope, for example?
Why is there what, sorry?
Why are there times there instead of like a slope? Or like
What is that time? 23 nanosecond. What is this?
It's how long it takes for them to relax from the excited state back down to the ground state.
But if it is exponential decay, it will never completely relax. So what is the just definition of this time? Is it like time that it takes to change occupation E times, 2.7 times smaller, or
Something half-life, something like
or
that.
half-life? So the question is how do these numbers are defined? Just look it up for true seminar.
Look for what?
Look up
Yeah.
for the definitions before the true seminar.
Okay, yeah. Okay, thank you. Yeah. So,
To answer it, if you take the first term in the Taylor series it gives like X over tau, and then you can fit the tau.
Okay.
Does that make sense?
Yeah.
So it's just like fitting a function to your data with like least mean square.
What is the physical term of that? Physical interpreter of that? It's not just a term.
Yes, but I wanted to give him how they got that number.
Hopefully, Leo, I answered your question on that.
Probably
You did a
not.
great job.
So there a huge difference in your conduction band and balance band in this case?
Excuse me?
Very huge difference in the conduction bands and balance band density. How does it affect in this case, in this process?
So for the lead-rich surface, there's more tends to be more of a density in the conduction band than say for the
Yes, so balance band is more dense, right? balance band is more dense compared to conduction band.
yes, it's you see more of a bigger peak in the valence band than the conduction band for pretty much both of them, but that's due to probably the iodide. I haven't looked into it essentially to see if using a other iodide such as like bromine or chlorine will if you'll see the same effects to that. So that's something to look into, but
Don't you have like 3 times as many iodide as you do lead?
yeah, but it's a substantial amount more iodides than you do, but is that probably the reason behind seeing them more?
That could be one reason.
Did I answer your question, Javed? Or you still have more? Or did it suffice?
Yeah.
Any more questions on this? So I guess for the final slide today, well, from what I have so far, is so one of the things they wanted to point out was that between 2200 to 2500 femtoseconds, there tends to be a strong intensity of adiabatic coupling, and they're trying to state this due to the accumulation of the methylammonium cation inside the cages. They're trying to say that they took snapshots of at each 100 femtoseconds, and you see the rotation of the methylammonium slowly over time, and there is some slight bending in the cage. So go back to this thing right here. The cage gets distorted as the methylammonium is rotating. So they're trying to say that is the cause for almost having a tenfold increase of non-adiabatic coupling compared to the lead-rich surface.
Not volts, millielectron volts.
Milli-electron volts.
It's 1,000 times smaller.
1,000 times smaller. Okay, thank you. So yeah, we're trying to just state that, and it's because of the non-adiabatic coupling that they rationalize the excited state population of methylammonium iodide to be much smaller than the lead-rich surface due to the non-adiabatic coupling and the rotating of the methylammonium iodide, which distorts the cage that the perovskite structure is primarily found in. And yeah, I guess that's pretty much it for today's.
So, what are your plans to include from the literature? What else do you plan to include?
Plan to include. I was gonna pretty much just look at a little bit more of experimental things and that regard non-adiabatic coupling, and probably talk a little bit more about radiative and non-radiative emissions. Try to find some literature on that, and I guess try to make a much longer talk. Just try to fill in the time because I'm pretty sure I'm at half time. I'd say that's probably a high estimate. I probably have 20 minutes. So yeah, probably find more papers like Levi said, trying to be able to explain the experimental side of things too, or not include it at all. But I'm pretty sure I'm still gonna get asked even if I do include, or they're just gonna ask how the method was and things like that. But yeah, get a much better understanding of this.
So, although this seminar is not on your results, can you go to the last slide of your results and quickly tell what is?
The last slide of the results?
Yes. Yeah. Tell what it is, and try to relate it to your literature review.
So this sort of ties back to the last paper I just talked about, where they took two different types of surfaces. My A surface is my cesium-rich surface, compared to my B, which is my lead-rich surface. So what you see in blue is considered to be holes, and what you see in yellow, the hot zones, or where the electron will be found out. So on my cesium-rich surface, it's stating that on the surface of my material, there tends to be holes, while the core of the perovskite has all the electrons incorporated into it. So for charge transfer, this is kind of a poor choice, due to the fact that whenever you apply a current to this perovskite, it will just encounter holes where, with none of the electrons actually being able to escape the core of the perovskite. While on my lead-rich surface, you see the charge. Yes, it's faint, but there is some electrons on the surface, while the perovskite tends to be more the whole, so whole complete 180 or 360 from the cesium-rich surface. So that's stating that the perovskite, in this case, is acting as an acceptor, while the ligands are actually accepting, or the donators, or yes, the donators. So they have all the electrons with them. And yeah. Any questions on that?
How would ideal result leading to perfect light emitter look like? Both of the surfaces probably have some deficiency and will be not ideal light emitters, but how would this diagram look for ideal light emitter?
So I'm pretty sure it looked like my figure B, where.
But would it be better if both orange and blue stay only on the perovskite and nothing will be on ligands?
Yes, because then the perovskite would act as both as an electron donator and a electron acceptor. So
it needs to be a light emitter, so electron hole needs to be in the same region of space to be able to recombine radiatively.
Okay. Guess I gotta look at my definitions a lot better. Thank you.
Do you plan to develop conclusion slide?
Yes, when I finally complete. Yes, whenever I finally have a complete talk. Yeah, because I guess I didn't really have as much time as I like to try to have a complete session, and have enough of the correct material for a seminar. So, yeah. Any more questions?
So I have a question that you gave me.
Yes.
On slide 6, you said goals, question mark. I still don't know what that means. Or what goals you have, really. Or goals or goals. So what would be like your goal that I take away from this seminar?
The goal for.
But he has to know what he needs to teach before he can get everything ready, right?
He told us he's not ready yet.
I understand, but that's why you need to know what you want to teach, and then you can investigate.
And your question can be interpreted in twofold. What is the what is the goal of scientific community? for perovskites. And what is the personal goal of Daniel in telling this seminar, or which part of?
Yeah.
So I guess as a goal of, as a community of scientists, the goal is try to reach set theoretical values of perovskites. But
Efficiencies, not
yes.
perovskites. Efficiencies.
Efficiencies. And for a goal, myself, I guess I'm more interested in the photovoltaic side more than anything. So, but then again, the papers I've talked about are pretty much LEDs, aren't they? But yeah, that's a good question. I gotta think about that too if I do reorganize my seminar. Thank you. Thank you.
More questions to Daniel? Or comments or suggestions?
I would just suggest pick one and then focus on like problems with known problems with them that the community is trying to improve those efficiency goals. So like defects in the materials, whether they're for photovoltaics or LEDs.
Thank you.
And I think your introduction is too long about the renewable energy, oil, coal, everything.
Yeah, if I do go through one side, then yeah.
You need to be determined what you need and what you need to focus on that.
Okay. Thank you.
And you probably need more than 4 papers to cite. Just
Yeah, like
no.
yeah, no, I know that much. Yeah.
50,
Yeah.
I've just had a busy week. Apologize for a really short seminar.
It's not my grade that will be.
Yeah, no, I know. More questions, concerns, comments?
So if you've told that your personal goal is more on photovoltaics rather than light emitting, so you may summarize just for yourself, maybe not as a presentation, what are the benefits and shortcomings in research of both?
Mm-hmm.
Where there are more open problems and where you potentially can contribute more to the research.
Okay.
Last call for questions. If not, let's thank Daniel. And Daniel is planning to collect written feedback and immediately implement it into his slides, right?
Yes. Of course.
Okay, meeting is done. Have a nice weekend. As usual, there will be a writing meeting, or not writing meeting. On coming Tuesday, there will be a collaborative meeting with the research group of Professor Burkhaus on theory and experiment merger. And in 2 Tuesdays, there will be writing meeting on methods for papers. Something will be next Friday here.
Someone, I don't know.
It will be announced.